Hi everyone, welcome to our online class on electricity and electronics at Paradise Business and Technology College. I am Mr. John Kaupa, the class coordinator. This is Unit 3, Ohm's Law, Energy and Power in Electric Circuit. We are going to look at Ohm's Law, electrical energy and power in a circuit. Okay, Ohm's Law. What is Ohm's Law? Ohm's Law is a relationship that governs voltage, electrical current, and resistance. So the person behind this relationship will work really hard to bring about the equation and relationship between current, resistance, and voltage is none other than George Ohm. George Ohm was born in Bavaria and he struggled for years to gain recognition for his work in formulating the relationship of current, voltage, and resistance. Okay, this mathematical relationship is known today as Ohm's law, and the unit of resistance is named in his honor. So George Ohm is the hardworking man behind this law, and that law is now used in the study of electrical engineering, electronics, and all the other principles built on from this basic uh, law of voltage, current, and resistance. Okay, let's look at the Ohm's law and the equation of Ohm's law. Ohm's law describes mathematically how voltage, current, and resistance in a circuit are related. Ohm's law can be written in three equivalent forms. The formula you use depends on the quantity you need to determine. So as you can see here, the triangle there, it's called the Ohm's law triangle. The first one, when you want to work out voltage is equals to current times resistance. When you want to work out current is equals to voltage on resistance. And when you want to work out resistance in a circuit, given voltage and current, that's resistance is equals to voltage over resistance. So it depends on which quantity you want to work out, okay, in a circuit. In words, Ohm's law states that current is directly proportional to voltage and it's inversely proportional to resistance, which means to say that in an electric circuit, if the voltage increases, the current will increase. If the voltage decreases, then the current will decrease. But for resistance, when it increases, the current will decrease. When resistance decreases, the current will also diminish. So current is directly proportional to voltage and is inversely proportional to the resistance in a circuit. Okay, let's look at some of the examples of Ohm's law here, if we can apply the Ohm's law equation to solve some of the circuit problems here. The first one here, you will see the circuit in red and black. The voltage source is 50 volts, the ohmic value of the resistor there is 10 ohms, and current there is not known, so that circle with the A in there means a ammeter. So we're placing an ammeter in the circuit to measure the current in the circuit. So using Ohm's law, current is equals voltage divided by resistance. So 50 divided by 10, 50 volts divided by 10 ohms will give you 5 ohms in a 5 amps in the circuit. So 5 amps. That circuit is a series circuit, so the current will be constant in all the components in the circuit. The second example there in green, we have 8 amps running through the circuit and we have 12 volts as a supply. We are asked to find the value of the resistance there. We have 3 sets of resistance there. Okay, so the combined value of the resistance will be the resistor value or resistance value of the circuit. So R is equals to voltage over current. So 12 volts divided by 8 amps will give you 1.5 ohms. So 1.5 ohms is the combined value of resistance of that resistance 1, resistance 2, and resistance 3 in the circuit there. Okay, so the total resistance of the circuit is 1.5 ohms. the voltage supply is 12 volts and the current running through the circuit is 8 amps. Okay, now let's look at the white one, white and black at the far end side on your far end side. You will see that the value of the resistor there is 200 ohms. The voltage supply is not known, and then we have current is equals to 5 amps running through the circuit. When you use the Ohm's law, voltage is equals to current times resistance. So when you multiply current by resistance, you will see that 5 by 200 will give you 1000 volts or 1 kilovolts. Okay, these are some of the examples to strengthen your knowledge about the Ohm's law and how you can use the Ohm's law equation. Okay, let's look at Ohm's law pie chart. Ohm's law pie chart is pictorial. Okay, it's a chart that shows all the formulas relating voltage, current, resistance, and also power and energy as well. Okay, so an Ohm's law pie chart or formula wheel is a visual reference tool used to calculate the 4 primary electrical parameters: voltage V or E, current I, resistance R, and power P. Okay, so all the formulas are given there. You will see current, voltage, power, and ohms. You will see they all have 4 sets of formulas that you can use to work out each of the quantities. Like current, you have 4 formulas. Current is equals to voltage and resistance. Current is equals to power on voltage, and current is also equals to root of power divided by resistance. Voltage is equals to power times resistance, root of power times resistance. Voltage is also equals to power on current. Voltage is also equals to current times resistance. Resistance is also equals to energy, not energy, voltage on current. Resistance is also equals to voltage square divided by power. Resistance is also equals to power divided by current square. For power is equals to voltage times current. That's the basic formula, but power is also equals to current square times resistance, and electrical power is also equals to voltage square divided by resistance. So this formula here derived from Ohm's law. Okay, Ohm's law, the basic Ohm's law. Okay, electrical power. Electrical power is the rate at which electrical energy is transferred or converted into other forms like heat or light within a second. Measured in watts, it is calculated as the product of voltage and current. So power can be calculated using voltage times current, or square of voltage in a second divided by the resistance of the circuit, or square of the current running through the circuit times the resistance of the circuit. So these are the 3 sets of formulas that you can use to calculate the power. Power is also equals to energy divided by time. Okay, energy divided by time is also a formula that can be used to calculate power. You can also put the power formula into a triangle. Power is equals to current times voltage. Current is equals to power divided by voltage, and voltage is equals to power divided by current. Let's look at an example here. This circuit here, we have a voltage supply of 24 volts. We have a current running through the circuit. That's 2 amps. Okay. The resistor there is a 12 ohm resistor. Okay. Power is equals to voltage times current. Okay. So when you multiply 2 amps by 24 volts, you get 48 watts. Okay. Or you can go the other way around. V square on R. 24 square divided by 12 will also give you 48 volts. Or you can go the other way around. I square times resistance, 2 square, which is 4 times 12, will give you 48 watts as well. So this is how you work out electrical power. Okay, this is an example here. Okay, we have a circuit there Actually, we have three sources of voltage there and one resistor or one load there. How do you go about to handle this kind of problem? Voltage are the force, so force, they have magnitude and direction. So when you see a lot of voltage sources like this, you add them in the order of their polarity. That 12 volts and 8 volts 18 volts there, they are in the same direction, meaning their polarity are in series. So when you add them up, you have 30. That 15 volts is opposing this two voltage sources, 18 and 12 volts. So you are going to subtract it. So when you subtract it, it's 30 minus 15 is 15 volts, which is the total supply in the circuit. And then you have 5 ohms there. So when you use the formula V square on R, you will have 15 square divided by 5. Okay, 15 square divided by 5 will give you 45 watts. So 45 watt of power being dissipated across this resistor, or is being used by that 5 ohm resistor. Okay, kilowatts and watts and kVA. Kilowatts and watts are also unit of power. kVA is also unit of power, but the difference is kVA is the specification of power generation, and kilowatt and watt are the specification of power consumption. So watts or kilowatts measures the actual power consumed by equipment to perform work, such as powering lights or motors. Kilowatt amps is still referring to power, because it's kilovolts amps is volt times amps, or current times voltage. It's also the unit of power. It measures the total power supplied to a circuit, including useful power and non-useful or reactive power. It represents the capacity of electrical equipment like transformer and generator. So the difference, to put it in simple terms, is watts and kilowatts are the specification of loads or electrical appliances or equipments that uses power, and kVA is a specification of the source of electrical power, like generator or transformer. Their specification or ability, or how much power they produce, or the generate or produce, is specified in terms of kVA, kilovolts amps, or it's also the unit of power on the generation side. Okay, voltage rating. Voltage rating refers to the amount of power an electrical appliance can use, like motor or light or aircon or whatever. They all have a power consumption rate. Like for motor, you will see them on the nameplate. For light, you will see them on the frame. You will see how much power they will consume. Our fluorescent tubes, we have, the long one is 36 and the short one is 18 watts. Okay, so basically all appliances or equipment that consume power as a standard or specific power consumption rate. Okay, what measure the rate of energy transfer? So basically power is the rate at which energy is transferred, okay, or is converted from one form to another. Like for our case here, it's from electrical to light, or from electrical to heat, like for aircon, or from electrical to motion, like for motor. Watt ratings indicates the power consumed by appliances or produced by a source, calculated as voltage times current. Common ratings ranges from low voltage electronics like 5 watt to 100 watts, or high power appliances like 1000 watt to 3000 watts. So as you can see from the other side there, the table there has a lot of appliances, and their voltage rating is also stated there. Okay, it's running voltage and starting voltage. So some appliances, they start at different power rating, because it needs a lot of power to start. Then when it runs at a normal specification. So that's what it means. But generally, of all appliances, they have their standard consumption rate of power. Okay, resistor voltage rating. Like we have discussed, all electrical appliances or any electrical load, they have a specific voltage rating or power consumption rate. Likewise, resistors also have voltage rating because resistors are also electrical loads. They consume power, or in other words, electrical loads, they take in electrical energy and they convert it to another form. Like for resistors, they convert into heat. Like for light, they convert into light. Motor, they convert into motion. So resistor power rating measured in watts defines the maximum heat a resistor can dissipate safely without damage. Generally, larger physical size correlates to higher power handling capability. So when you see a big resistor, that means its power capacity or voltage rating is greater. When you see a small resistor, then the voltage rating is less, smaller. Okay, the unit of power is watt. The unit of power watt is named in honor of that fellow there, James Watt. James Watt was a Scottish inventor. He was born in 1736. He passed on in 1819. He was well known for his improvements to the steam engine, which made it practical for industrial use. The unit of power is named in his honor. Okay, steam engine. Remember this Titanic video? You will see some workers at the bottom deck. They are bending coil. Okay, they simply bend coil to generate heat to run the engine of that ship at that time. So, Titanic is a classical example of a steam engine uh, ship, and then trains and other automobiles also use steam engine at that time. That was James Watt's invention, so that's why they named the unit of power in honor of him, Watt. Okay, electrical energy. Energy in physics can be different types of energy: potential energy, kinetic energy, mechanical energy, chemical energy, whatever it is. But in our study, we are focusing on electrical energy. In physics, the basic definition of energy is a ability to do work. Okay, energy is the ability to do the work, and power is the rate at which energy is used or transferred from one form to another. Okay, in other words, power P is a certain amount of energy or work used in a certain length of time. Okay, expressed as follows: energy is equals to power times time, or power is equals to energy divided by time. Or you can use the small triangles there to rearrange and find out whatever quantity you are required to. Okay, so basically in the context of electrical, when the voltage are applied to the conductor, they move the electrons within the conductor. So according to second law of motion, force is equals to mass times acceleration. You need to apply a force to accelerate an object. When the object is accelerated, there is work done. Okay, so in that context here, when the electrons move, there is work done in the second. There is a transfer of energy. Okay, so you can work out that energy. So the formula is energy is equals to power times time. Okay, let's see how we can apply our knowledge on energy, power, and Ohm's law here to work out the problem here. Calculate the total energy supplied by the batteries to the circuit shown in the figure in 1 minute. Okay, in such circuit here, at first it's really difficult to work out the total power and the energy, but the way out is always add the voltage sources. We have 4 and 10 volts in the circuit there. There are two different sources. When they are connected in series, you just add them up, but also consider the polarity, the direction of the voltage. That 4 volts is opposing the 10 volts there, so you're going to subtract 4 from 10 to get the total voltage. So total voltage is equals to 10 minus 4 is equals to 6 volts. Total resistance, because all the resistance is connected in series, you add them up. 3 plus 6 plus 1 plus 2 is equals to 12 ohms. Total current in a second is equal to total voltage divided by total resistance. So 6 divided by 12 will give you 0.5 amps. Power is equal to voltage times current, so you will multiply 0.5 by 6 will give you 3 watts. Or you can do it the other way around. Power is equal to voltage square over current. 6 times 6 divided by 12 is equal to 3 watts. Now you can calculate the energy used up by the circuit, or convert it from one form to another, like from electrical energy into light or whatever it is. Power times time is equal to 3 times 60, that's 180 joule. So what it means is, across these 4 resistors there will be 3 watts of power used by these 4 sets of resistor. After 1 minute, okay, you will have 180 joule consumed. So that's where we have 60 seconds there. 1 minute is 60 seconds, so energy is equal to power times time. 3 times 60 seconds is equal to 180 joule. So 3 watts of power dissipated across these 4 resistors, and after 1 minute these 4 resistors will consume or will use up 180 joules of electrical energy. Okay, energy meter. Like other physical quantities, they have an instrument and meter that measures their value, magnitude, and their size. We also have energy meter that measures energy. An energy meter is a device that measures the total electrical energy consumed by a building, machine, or appliance over time, typically in kilowatt hour (kWh). It is essential for billing, monitoring power usage, and optimizing efficiency in homes and industry. So, like our ECP meter is a single-phase energy meter. We also have 3-phase meter for industries and all this. It measures how much energy or electrical energy consumed by our electrical appliances and our electrical circuit at home, and work out the cost that we are going to pay to PNG Power. Okay, the unit of energy, joule, is named in honor of this fellow here, James Prescott Joule. He was born in 1818 and he passed on in 1889. He's a British physicist. He is known for his research in electricity and thermodynamics. He formulated the relationship that states that the amount of heat energy produced by an electrical current in a conductor is proportional to the conductor's resistance and the time. The unit of energy is named in his honor. Okay, that brings us to the end of our unit 3 on electrical power, electrical energy, and Ohm's law.